Now that we've seen the overall idea behind forwarding, we're ready to make the modifications to our pipeline diagram. So here's a general diagram of our LC3 pipeline. And let's just review all the different stages. So first we have instruction fetch, where we read an instruction from the instruction memory. And then we have a set of flip-flops here. We have a register. It's a pipeline register, which is clocked on the rising edge of the clock. So in the next tick of the clock, that instruction moves to decode. And in decode, we read the source registers. Next tick of the clock, we move into the execute stage, where for an operate instruction, we do the operation. For a load or store, we calculate the address. Next tick of the clock, we get to the mem stage. And here, for load or store, we actually do the memory operation. And for other instructions, we just bypass this stage. And then finally, on the last tick of the clock here, is the write back stage. Now what I've drawn here is I've actually drawn the connection back to the register file. So in our pipeline diagrams, we've had this other register over here, register file picture. But of course, we only have one register file. So I'm actually showing the real connection back to the one register file to do the write of the destination register. Now what I have here is I have our instruction sequence that we just saw. So let's just go over that again. So the first instruction in our sequence, and we're assuming that this is in the mem stage, is an add instruction, and that add writes to register 1. Right behind it is a not instruction that reads register 1. Now it read this value of register 1 back here in ID. So it has the old value of register 1. It doesn't have this value, and this is our data hazard. This is our problem. Also in the ID stage, we have this AND instruction where we've also read R1 here, and again, this is an old value. This isn't the value that we want. This is the one that we want. And then back here in the instruction fetch stage, we've just read this LDR instruction. Now it also is going to read R1 in the decode stage in the next tick of the clock. Okay, so you can see our problem where we're about to do this NOT operation with an old value of R1. Where we need to do this NOT operation with this value of R1. So we talked about forwarding, how we can pass, how we can pass the value from the mem stage to the execute stage. And so we're going to draw a connection back here, backwards, in order to forward this value to this NOT instruction. So what we need is we need a multiplexer in order to do that. So we read R1 from here. This is the first source register. Okay, this is where we read the first source register. So we're going to substitute this value for this value that's sitting here in the mem stage. So in order to do that, we can just put a multiplexer. So we're going to add a multiplexer here. We still have this value because we may need it for other situations. And now we're going to take this value of R1 that we have here. Okay, so here we have the result of the add. We have it right here. And we're going to tap off that here. And we're going to feed that back here to this multiplexer. Okay, so now we also need a select signal. And this will be part of our control now. This is an additional part of our control, is to pick the proper one of these two. Okay, depending on what their dependencies among instructions in the pipeline. And so now we have the capability of taking this value of R1, and at this tick of the clock, we're going to pass it back here and replace it for the value that just got loaded into this flip-flop, this set of flip-flops. Okay, and so we use the select signal to pass this value to the ALU, and so now the NOT can be performed properly. It will get the correct value of R1. Okay, now let's see what happens when we advance one cycle forward. Okay, let's move this one cycle forward. So I'm just going to draw these like this. Add R1, R2, R3 is now moved into write back. The NOT is here. We have NOT R4, R1. The AND has moved here. We have an AND R5, R2, R1. And our LDR now has moved into the decode stage. We have LDR, R6, R1, 0. Okay, so one tick of the clock later, this is the situation that we have. Now the NOT is all set because in the previous cycle we forwarded the correct value of R1, we've inverted that, and now that's sitting right here, so the NOT has been properly executed. But now we have the same problem with this AND. This AND has read an old value of R1 in the previous cycle. It's about to use that to do this ALU operation. Okay? And so what we need to do is we need to forward the value that's in the write back stage of R1. We need to forward that back here. Okay? So now R1 is the second source operand. It was read down here. So we need to substitute this value of R1 that's being written to the register file for this value of R1 that we're about to use for the ALU operation. So we need to add another multiplexer right here in order to accomplish that. Okay, so let's add that multiplexer. So what we're going to do is we're going to take this value of R1, which is being written to the register file, and we're going to substitute that like this. Again, we need another select signal. Okay, so now when this AND instruction moves into this execute stage, we're going to set this multiplexer so that the value that's being written back to the register file, R1, is going to pass through the MUX and be used for this AND operation. And now this AND will operate correctly. Okay? So now we've got the NOT all set, we've got the AND all set. Well, what about this LDR? Okay, this LDR has just read the old value of R1. Again, this is the value that we want to use in order to form the effective address. So we have a problem here because our last chance, okay, we've just read R1, and we're about to write now R1 to the register files. This is kind of our last chance to substitute this value of R1 for this LDR. So we need to do that in this stage, in this ID stage. Okay, we need to replace now this value of R1. Okay, so we need to put another multiplexer here. Okay. So that, again, we've read the old value of R1 here for this LDR, and we're going to, again, substitute the value that's being written back to the register file for that value that we just read from the register. So now when the LDR moves into this stage to do the address calculation, it has the up-to-date R1 from the add instruction. So now all of these three instructions are going to operate properly. The NOT will have been forwarded, gotten its R1 value forwarded here when it was in the execute stage, and the add was in the memory stage. And then when the add moved to the write back stage, it forwards the correct value to this AND instruction through this bottom MUX, and also to this LDR through this MUX here. So now all of these are going to operate properly. Now, we may also need to forward from here, okay, back to this value, okay, rather than here. So we need to also forward, in addition to here, we also want to add some forwarding to this lower input, because it could have been that we had an instruction that was here writing R1, and then this instruction here read the second source value was R1. So in that case, we need to forward R1 to the bottom input of the ALU. And similarly, for this forwarding path, where we only come here to the bottom input of the ALU, well, we might want to also, and I'm just going to modify this slightly so it's consistent, we also may want to forward that value to the top input of the ALU. So we need to have also this value here coming to this bottom input as well as this top input. So now we can forward from here to either the first or second source operand, and the same for write back. We can go to the top or we can go to the bottom. And then we might want to do the same thing here. There may be an instruction here, such as it could be this AND instruction, let's say if it was over here, okay, then we need to substitute down here. So we can make this multiplexer. We can add an additional multiplexer here, I should say, so that we can forward from the write back stage to either source 1 value that we just read from the register file or for source 2. So now we have all of the data path that we need in order to do forwarding of this situation where I have an ALU instruction, such as this add, where we need to forward the values back to the other instructions. Now it gets a little trickier when we have LDR instructions that need to be forwarded, and we need additional hardware for that. Okay? And so you can expand this diagram to also handle ALU operations, I should say load and store operations. But also you need to keep in mind that there's all of these control signals. So there's a number of control signals here where now our control, which we do in this pipeline, has to be able to detect these dependencies dynamically. So as instructions move through the pipeline, we're doing comparisons of destination registers, like R1, with source register numbers that are behind this instruction. So there has to be some comparators and these multiplexer controls to make sure that the proper value gets input to each of these multiplexers dynamically as instructions move through the pipeline. So once you have this data path and you have all that control, then now you can avoid the problem where you get the wrong value, like we would without this kind of support, or where you just had to stop the pipeline and wait for the register file to be updated, in which case you lose performance. So here we get both correct operation as well as high performance with this forwarding hardware.